The Energy Institute guidelines are a set of guidelines that are used to proactively assess vibrational issues of pipework. These guidelines can be used to assess new designs, existing plants, changes to existing plants, and potential problems identified on operating systems. The Energy Institute uses various calculations and flowcharts to evaluate the likelihood of failure for a specific pipe in response to a specific excitation mechanism. The end result of the calculations is the likelihood of failure value, or LOF. The LOF value is a form of scoring for screening purposes. However, do note that the LOF score is not an absolute probability of failure nor an absolute measure of failure. The pipeline users/owners are responsible to determine the level of mitigation measures to be implemented by comparing the criticality of failure versus the resultant LOF. The Energy Institute has some recommendations on the actions to be taken dependent on the LOF. The background for the Energy Institute guidelines is empirically based, using experience, simplified models, and real-world examples to develop a basis for the calculations developed and the LOF results. Due to this empirical background, the calculations are oft necessarily conservative. The AIV screening procedure follows flowcharts T25 and T26 and consists of the following steps, where we first evaluate the sound power level of the source, including any noise trimming fittings, as well as accounting for the sonic flow correction factor, the SFF in the equation there, as well as the next step is then to determine if the source is less than the allowable of the Energy Institute, being at 155 decibels. Then the LOF of 0.29 is used. If the sound power level is greater than 155 decibels or equal to 155 decibels, then we continue on to the welded discontinuity screening. The welded discontinuity screening accounts for the attenuation of the noise as it travels downstream to the nearest weld location. This is where failure is likely to occur, if we remember the theory previously. Noise can approximately be reduced by about 3 decibels every 50 times the pipe diameter. To account for the next step is to account for all AIV sources acting on the weld and the attenuation thereof from the sources. And then lastly, if the sound power level still remains above 155 decibels, then we perform a high frequency acoustic fatigue assessment to determine the LOF at the welded discontinuity. For the FIV screening procedure, we follow flowchart T21 in the Energy Institute, where we first of all determine rho v squared, followed by a fluid viscosity factor. If the system is liquid or multiphase, this fluid viscosity factor is 1. And then we determine or evaluate how stiff our support arrangement is. And we classify the stiffness in several categories: stiff, medium, or flexible. This evaluation can be done through assessing the line's natural frequency or through a span length criteria calculation. The fourth step is to determine the flow induced vibration factor, FV, with consideration to the support arrangement stiffnesses. And then lastly, we calculate the LOF score of the fluid induced vibrations. For periodic flow induced excitations, the screening procedure follows flowchart T24, and this procedure begins by determining the critical diameter of the dead legs, and then we evaluate the inner diameter of each dead leg and compare it to if it is greater than or equal to the critical diameter. If so, then we continue to calculating the Reynolds number, and then determining the S, Fy, and Fv and Fs parameters. We then evaluate if Fv over Fs is greater than or equal to 1, which then results in the LOF score. Upon determining the LOF, action points are advised by the Energy Institute depending on the band in which your calculated likelihood of failure falls into. The actions can vary between visual surveys, vibrational measurements, or line redesign, and should be considered with regard to the criticality matrix of the likelihood of failure against the consequence of failure.